And it gave me a glimpse at what was the challenge within this market: expensive licenses, expensive hardware, and thus expensive consulting services to get a simulation done. So back then, I quit my job when traveling for a few months in South America. When I came back, I needed a job. So I just applied at that agency, asked me, can I just work here? And they said, that's fine. And 2 weeks later, I was actually there for my first day at work.
Hello and welcome to this brand new episode of the Driven Engineers podcast by MatchTech. In today's episode, we'll be taking a closer look at how aerodynamics is becoming more accessible to engineers and designers across different industries. Our guest is Wouter Remmerie, founder and CEO of AirShaper, a platform that simplifies aerodynamic simulation and helps teams understand airflow earlier and more easily in their design process. We'll talk about Wouter's engineering background, what inspired him to start AirShaper, how digital tools are changing the way products are developed. It's a great insight into a practical side of aerodynamics. So let's say hello to the man himself. Hello, Wouter. How are you?
Oh, doing well. Hey, Matt. Nice to see you again.
Good to see you too. So I always do a little introduction to our guests, but I don't know if you want to just give yourself your own introduction. I think it's always nice for you to introduce yourself to our listeners.
Yeah, happy to. I'll keep it short. So I'm a mechanical engineer, actually, by training. And I first spent a few years designing gearboxes, not for cars, but for wind turbines. So huge gearboxes, like one gearbox would weigh 60 tons or something. And then in my free time, I designed the car, and that's how I rolled into aerodynamics and got the whole AirShaper track going. That's a very short description.
Perfect. We'll dive into a little bit more of that. But so let's start right at the beginning then. This is a careers podcast. So let's start right at the beginning of your career. Where did your passion for engineering, particularly aerodynamics and motorsport and automotive, but where did that spark first come from?
Yeah. Well, I guess I'm definitely not unique in this regard. I was playing with Lego Technics when I was a kid, and I like playing with gears and making all kinds of new cars using just the same building blocks. And then this just kept going. Then as a kid, I joined my dad going to 24-hour races within Belgium, but also beyond, went to Le Mans and so on, which is all very interesting. And then when I had to make a career choice after, let's say, high school, I just went for mechanical engineering. Because I liked that stuff, and it was just really nice. First 2 years were a bit tough because it was very theoretical in Belgium. Let's say the bachelor's track. It wasn't called bachelor back then. But afterwards, we got more into the more pragmatic or practical stuff. Like we had like a project where we tuned a kart engine, for example, by changing the length of the exhaust system, because then the negative under pressure wave, which is reflected at the end, helps to draw in more air into the engine. Things like that was really nice. And then I continued along those lines, which was to develop gearboxes. So I did casting design and so on for ZF, which is a large German gearbox manufacturer. I do plenty of things.
Yeah.
And then at some point, a colleague and I decided, well, let's design our own car, right? But that was around the time of the financial crisis and so on. So there were layoffs. He was let go. So I just continued on my own. And the goal was to, I don't know where this came from actually, but to use internal and external air channels to make a car go faster through the corners by generating lateral forces, left and right, rather than downforce, which pushes the car on the ground. And that's how I started tinkering. I still have the very first dodgy clay model. So I guess this is how everyone starts out.
Fantastic.
This is like 17 years old or something.
I love that.
I just carved some channels at the bottom of the car. The next step was to just gather a whole bunch of pictures of car chassis to see whether I could fit those channels inside. And then I designed this one, which is, well, you can't accuse me of stealing any McLaren design cues because this was before McLaren, but this was the 3D printed version of that car where air would go in at the front and then exit at the sides, go in again at the sides, and then exit at the rear. Also
That's
had some double
fantastic.
diffuser going on. So it was started as a hobby, passion project, let's say, which is great if you can build a business on that premise, let's say. And then I played around with kind of 3D printing. This is a chassis that I designed for the car. This was the render of the car. And to take this to the next level, because this is just a hobby project, I contacted a service in Belgium here, which helps you with innovative ideas. They pointed me to an engineering agency in Antwerp, in Belgium, where I live. And they told me, go talk to them. They might be able to help you. Because I had the 3D model of the car, they said, well, we can run simulations for you, but it'll cost you 3,000 euros.
Wow.
That was way too much as a hobbyist to just go ahead with that.
Right.
And it gave me a glimpse at what was the challenge within this market: expensive licenses, expensive hardware, and thus expensive consulting services to get a simulation done. So back then, I quit my job when traveling for a few months in South America. When I came back, I needed a job. So I just applied at that agency asking, can I just work here? And they said, that's fine. And 2 weeks later, I was actually there for my first day at work. And we did two things. One was to develop this project as a parallel side track, let's say, where we went for a patent. So we teamed up to get this patented. And we got the patent. It was granted. It was thought to be innovative enough, and then all of those requirements. We got the patent, and then Ferrari referenced to our patent in one of their patents. So did Toyota, Faraday Future, and so on. Which got the ball rolling to start talking to these companies, which is really nice. I talked to one of those aero gurus at Ferrari, and then I got to visit Pagani at their head office in Italy, which is really nice. So extremely rewarding track. Also got feedback from Louis Vermeers, who's a very renowned car designer. Used to work at Pininfarina and so on. That was really cool, but then in the end, that project kind of stopped because the channels I was designing were taking up too much packaging space. But that is how I got into aerodynamics. I didn't study aerodynamics. That's how I got into aerodynamics based on some passion. And then the coming 6 years, I worked on all kinds of projects within that engineering agency where I started working. And we looked at the aerodynamics of NASCAR, IndyCar, drones, solar panels. Back then, it was the big boost in terms of solar. So everyone was putting solar panels on their roof, companies, individuals, and so on. But they sometimes would fly off because the wind loads are huge on these things. As you can imagine, they are just wing profiles waiting to be lifted, right? If you don't position or anchor them properly. So we're doing a lot of work in this domain. Plus, we also went to some wind tunnels where we wanted to validate our simulation results and correlate them to wind tunnel data. Because if you don't trust or believe your simulations, it's hard to actually design a product or make something safe. So we also did wind tunnel tests where we would instrument the solar panels with pressure taps and so on, run at different angles of attack just to correlate the data. And we saw a nice correlation. And that's how I got into the aerodynamic simulation scene for about 6 years, doing projects myself, doing the project management of other projects and so on. And then at some point, I wanted to do something with the car that I had designed. So I joined one of these tracks, which you have in many countries, which support you on early stage ideas. And they recommended that instead of, because what I wanted to do was to be a coach builder, like Bertone or Pininfarina and so on in the old days, where they would just take a standard car, make a custom car.
Yeah.
Well, my thought was, I'm going to make a custom car with an aerodynamics touch, right? Okay. That's going to be my unique selling point. And then someone who was guiding me with this, with these ideas, on these ideas, she said, well, maybe this aero touch can be the essence of what you're offering rather than the cars. And then this created the idea of running an online wind tunnel, where people could just upload a 3D model to the web and analyze the aerodynamics without needing to be an expert. So I pitched that idea to another incubator for slightly more advanced ideas and concepts for a business. I got accepted, but this was all after hours, right? This was 2015 when I got accepted. Yeah. Which means I was working full time, had one kid already, second on the way, a house to pay, and so on. So I wanted to go full time, and the way out for me, or the way in for me, was to find a way to still be able to live and do this full time, which in my case meant gathering funding, which ended up being a mix of government funding and private funding,
Okay.
and then jump. So after 2 years of prototyping, I gathered all of the funding. Everything came together. The government said yes, the investors said yes, and so on. And then we hired the team in 2017, and we kept on developing the prototype, the small prototype that I had built with the help of some other people as well. And then we launched the first version of the platform in 2018. And what I wanted to do with AirShaper is to solve the issues that I was facing every day myself as a consultant or as a hobbyist 10, 15 years ago, which was, if you want to get into aerodynamics, it's prohibitively expensive and difficult in many cases. Unless you have 50,000 euros for a software license, one license, a few
Wow.
10,000 euros for hardware to actually run the simulations, and 100,000 euros a year for a trained engineer or someone with an equivalent background to run the software. Unless you have that and you're going to do this day in, day out, it actually doesn't make sense to start doing this yourself this way. I really like those software programs. They make total sense
Yeah.
if you do it every day. But if you're a small company or if you're a motorsport team and you're working on aerodynamics 3 months out of 12, and the other 9 months you spend building the prototype, testing it on the track, and actually racing, then it doesn't make sense to make this huge investment.
It's a big
Yes,
expense.
exactly. And even if you have the software, I was spending half my time, I'm not exaggerating, I was spending half my time fixing the 3D model of the customer. Not
Really.
that the customer wasn't able to provide a proper 3D model, but the 3D models need to meet certain quality standards for most traditional CFD software, which is the models need to be watertight. So you need to close every single gap and hole. So if you're working with a 3D scan, it's usually full of gaps and holes, or it's been made watertight and they
Nothing.
closed gaps which weren't supposed to be closed. So you will spend days, weeks, sometimes even months preparing a model for CFD simulations.
Wow.
So there's the preparation time, then you have to wait for a license, you have to wait for the hardware. Once it's all done, you have to put time into making images, making visuals out of the data that you get. And so this entire process is very time consuming.
Mm.
So what we did with AirShaper is to flip things around. You don't need software, you don't need hardware, and you don't need expertise because we automated everything. You just upload a 3D model to our platform. You set the basics like how fast is your car going. You hit one button to select the wheels. They will start spinning. And behind the scenes, even though this feels like a very simple interface, and it is, the calculations are top level. Because we've implemented all of this expertise that we've built over the years, including adaptive mesh refinement, which will increase the resolution where the flow is most detailed or most turbulent and so on. All of these images, the post-processing is all done in an automated way, drastically lowering the threshold for teams to get into aerodynamics. Whether you're a race team or building drones, we've done the fastest drone on the world, on the planet, and so on. It's become extremely accessible to that level, to that extent, that on our free plan, which is community simulations, which anyone can see, we even have 12-year-old, 14-year-old students running aerodynamic simulations now because it's completely automated.
That's fantastic. I mean, those costs have just blown my mind about how much that costs over, like you say, a 12-month period, and they're only using it for maybe 3 months of that. That is, I didn't realise the cost involved in that. So that is a big part. You've kind of done it there already, but for our listeners who are brand new to AirShaper, can you give us the elevator pitch? What exactly is AirShaper? How does it make aerodynamics easy for engineers, designers, people that want to get involved?
Yeah. I've prepared a sample project. Maybe I'll just share my screen, if
Sure.
that's okay. And I can
Yeah,
just show
sure.
you. That's the best pitch I can ever give, right? So I'm just going to share my screen. And whenever my screen is visible, just let me know.
Yes, can see that. Yeah, perfect.
Okay, fantastic. So we've reduced the effort to set up a simulation literally to one page, which is what you see here. And whatever you need to set doesn't revolve around specific simulation settings. It's just general stuff like, is your object on the ground or above the ground? If you do a drone or an aircraft, it'd be flying. This car is on the ground. Is it static or moving? Which means static is a building, moving is an object like this one. Is it air or water? As simple as that. You specify the velocity. I've put 120 here just to stick to the legal limits. On the road, you orient your car so you can do yaw angles and so on to position your car correctly. You select the units, and that's it. If you want, you can also add wheels. So what we've done, because I make this mistake myself many times, is when you select a rotating wheel, you have to define a coordinate system, axis of rotation, direction of rotation, and so on. So too often I would come back after the weekend and I would see that my wheels were spinning the wrong direction or around the wrong axis. So that really sets you back. So our algorithm, like you just saw, I clicked one button and it automatically detects the wheels. It detects the axis of rotation. It shows you in which direction the wheels will be spinning. Of course, not too fast, otherwise you wouldn't see the spinning direction. And we calculate the RPM because we know the diameter automatically as well. And that's it. If you want, you can also add radiators, which means we can calculate the flow rate through radiator and so on. And on the next step, the only thing you need to do is to select an accuracy. We have 3 predefined levels. So 1 million cells, which is the resolution, which is just for students and hobbyists, very coarse, but gives you a first indication. We have a regular simulation, which is 10 million cells, which is what we use for the bulk of our work when we are building aero maps for race teams and so on. And when you want to sign off a design or prepare for a wind tunnel or really capture small details like the small gap between a multi-element wing and so on, you have an advanced simulation. And once everything is done, and we'll make these projects public so you can share them with your audience. You just get an online representation of the outcome. So in red here, you can see the what we call pressure clouds. It's an isosurface of total pressure coefficient of 0. This one indicates where you're losing energy, so you can really immediately spot like the headlamps here, for example, or small design cues which are tripping the flow. The front splitter is causing flow separation. You can see the mirrors, the A-pillar vortex, anything is just visible within just 2 to 3 hours at mid-level accuracy. These are the pressure maps. You can see how the front splitter is doing its thing. Low pressure areas around the A-pillar. You can spot areas of flow separation where the flow detaches from the surface by looking at the surface friction. So in the entire rear is detached flow. You can check how much momentum and attached flow you have on the underfloor of your car. If you've got streamlines which you can move dynamically, just understand the way the airflow curves around the car or even underneath the car to study the underfloor aero. We have a rough indication of the wind noise, which we've applied for OEM projects to study the wind noise of mirrors and so on. And we calculate the drag coefficient, the lift coefficient, the front and rear aero balance on your car. Everything is automated. And you can just click on components to analyze the forces on each individual element. So literally a 5-minute setup time and literally 0 effort to start analyzing and understanding your design. That's basically the essence of AirShaper.
It's really good. That's really, really interesting. The just out of interest, then, I mean, there are some big hitters in that field. I'm talking sort of ANSYS, Fluent, Siemens, PowerFlow. What scenarios would an engineer choose AirShaper first? I mean, you've already mentioned how quick and easy it is to set it up. Are there any other kind of points that might be beneficial to somebody rather than going into using one of those others?
Yeah. So one of the key aspects is consistency. If you're running simulations on concept A, B, C, D, if you want to rank them in terms of performance, consistency is key. Because if you have 2, 3, 4 people working on the same project, and I was exactly the same. When you get a new computer, when you get a new software, you just want to max it out, right? I have 20 gigabytes of memory. Let's just make the mesh as big as we can on 20 gigabytes of memory. So within companies, within larger companies, our big benefit is that we make a completely standardized workflow so that whether it's person A or C or F running simulation, you can just compare the results 1 to 1. The second thing is that we help you save time and money. So time, we saw it's a 5-minute setup time and it all runs on high performance computing. So it's done within hours. You don't have to struggle for extra licenses. You can launch 20 simulations in parallel. You can build a full aero map of a race car within 4 hours. Literally. If you have the 3D model, that's all it takes. So we provide dramatic increases in speed, development time. And if you're in the racing business, as you know, this is key. We work for example, for Brazilian stock car racing. As soon as they get the new car, they get to work, need to scan it, need to make a 3D model, need to aero map it, and so on. With our platform, that's just 10 times faster than conventional software. And as you mentioned, of course, we did lower the barrier to get into aerodynamics dramatically. So for most companies, the answer is, well, let's just not do aerodynamics at all. We're developing a helmet. Safety. Let's do safety, but let's just forget about aerodynamics. We're developing a motorbike. Okay, fine. Let's just forget about aerodynamics. But you're leaving out performance. You could increase your range by 5, 10, 20% if you work on an electric car or race bike, for example. And for startup companies, this makes the difference between being average and being really a compelling product in the market if your range is 20% higher, which we did for many companies. Like we've worked for Aptera, which is a solar-powered electric vehicle. They have one of the lowest drag coefficients in the world. We worked for Twike, which is a three-wheeler in Germany. With our software, they cut the drag coefficient by 29%, which is dramatic.
Wow.
But
Yeah.
we've worked on custom Lamborghinis where a customer wanted a one-off, and the goal was to hit a very high top speed. And we reduced the drag of the donor Lamborghini Huracan by 27%, which is incredible. And that allowed us, or allowed them, to race the car on their first test, where the goal was to hit 420 kilometers per hour. They actually hit 447 kilometers per hour on their first test,
Fantastic.
just because we were able to cut the aerodynamics by so much. And that's where we provide the difference.
Yeah. Just another example as well. Luca Di Grassi recently used AirShaper as well.
Yes.
I talk a little bit more about that. He redeveloped or redesigned what he thought that was an F1 car. I mean, I'll let you explain. You could explain it much better than I can.
Yeah, happy to. So Lucas contacted us and said, we want to make a concept car, a vision for what Formula E could be in terms of performance, and the goal is to beat a regular Formula One car around the lap of Monaco, and that was the goal. And actually, we could actually do this theoretically within the digital world already, because if you have your drag coefficient, your downforce values, and so on, you can just throw that into a lap time simulation program and prove that it works. So we had implemented advanced concepts like suction cars, you know, the McMurtry, for example, and so on. Really cool cars, and we just bundled all of those cool technologies into one concept car that allowed us to actually hit that target. So there's a fan on the car, there's different aerodynamic elements. We completely restyled the car in terms of which elements go where and so on, ride height analysis and so on. So all of these things were analyzed, fan on, fan off. What does it mean? How much power goes to the fan? How much would you increase in top speed if you feed that power to the fan, or if you feed it to the electric motors and so on? So that was the vision, the DGR, which is the Di Grassi Formula E vision, and we continue to build on this, by the way. So that was that project where we took a digital approach together with Sébastien Lamour, who's working on the design of the car to actually make it a reality. And that's usually the thing with racing. You sometimes have to show people the vision. Because you can just mention to someone around the table at lunch, well, let's just make a car which is faster than Formula One. Fine. And everyone will say, yeah, that's cool. But how? But if you can then plant the vision and just show them how, like we've done the calculations, this is how it could be possible, then people start believing, and this gains momentum.
Yeah.
And that is what Lucas is doing. He's creating momentum, creating attention for his project. And then people get on board, start to believe, and go for the next phase.
That's great. That's really good. So just out of interest then, how accurate are the results compared to a physical wind tunnel? What key outputs do users get? Drag, lift, downforce, noise, pressure? I know you mentioned all that earlier on, but yeah, how accurate are they in real terms?
Yeah, that is the key question that most people ask. And the hard engineering truth, if you have to be really honest, is that you never really know upfront. That is the real hard engineering answer, because every geometry is different. And I'm not talking about AirShaper, I'm talking about any simulation out there. You never know exactly. But over the years, of course, you build up confidence, because users have a right to know, of course, which ballpark accuracy they can expect. We run validation cases with our code. Now, what we do with validation cases is that we have provided our software to our customers. They run simulations, and we get independent feedback from them. And the nice thing is that we don't tweak our code depending on the target segment. Whether we're working on high or low Reynolds flows, whether we're working on internal pipe flow, trucks, drone aerodynamics, low-speed fighter jet applications, or race cars, it's the exact same code base. So many people use this across different disciplines. They provide us with wind tunnel data, which was gathered by them, so not by us, which makes it independent and unbiased. And if it is biased, it's usually a skeptic bias, because the customer wants to kind of check whether your stuff is good. So there's actually a healthy skeptic bias in the beginning, and then they provide us with the data. We compare these graphs, let's say, so a lift curve or a drag curve and so on. And then we provide these cases as public data, at least whenever we have the authority to release this data. And we provide this in the form of validation cases on our website. Now, that's the long story short. To answer your question, we also go to the wind tunnel with cars, which is the topic of today. We recently went again to the S2A wind tunnel, just outside of Paris, where we have an office as well. We got within to, let's say, 6% deviation from the actually measured drag coefficient on a Tesla Model Y already 5 years ago. We got a very precise 3D scan of the Tesla Model Y, and we got the wind tunnel test data. So less than 6% delta between the two. And in reality, the delta would be even smaller because the wind tunnel only had a partial moving belt in between the wheels. With a full moving floor, the drag gap would have been even smaller. So that's just one example. We did propeller validation cases because we also work on propellers for drones, where we got within 1% of the measured thrust value of a propeller compared to our simulation predictions for the thrust. When we work on trucks, the European Union actually has created regulations that stipulate how accurate your software has to be before it can actually use it to quantify the gains of, let's say, flaps at the back of your trailer and so on. So they provide standardized 3D models of a standard truck, a truck with skirts on the side and so on. You have to run simulations at high resolution, and then you have to deliver your output, and that output has to be within predefined error bands that they control. And we're spot in the middle of those error bands. So whether it's pipe flow, trucks, drones, race cars, and so on, we consistently have good correlation results. One of the reasons for this is that the adaptive mesh refinement that we implemented will run a simulation at, let's say, normal resolution. Once that simulation has finished, our algorithm will inspect every cell in that 3D domain and inspect how high your gradient of pressure is, for example, which is typically high around airfoil elements, wing elements, and so on. How much vorticity you have, which is how much swirl you have in the wake, for example. And capturing the wake is really important to get a highly precise reading for your drag and lift coefficient. So this adaptive mesh refinement will locally increase the resolution where it's most required for your target, which is to calculate those values. And then we continue the simulation with this very dynamic mesh generation method that we have. And then we continue the simulation, and that's the final result we deliver to our customers. So when you're running a race car, if you're running the exact same race car at a yaw angle, for example, the flow results will be different, which means our adaptive mesh refinement will create a different mesh around the same car geometry, just to tune it to the new physical conditions that we see in the simulation. And that's how we are able to deliver consistency and highly accurate results on a consistent basis for our customers.
Brilliant. I think that's really important, isn't it, with motorsport as well, or any industry, really, making sure you're consistent and accurate, which is great, fantastic. There's one feature that I wanted to talk to you about. You were kind enough to lend me some logins to have a play around with the system. But there was one feature that I wanted to talk to you about, which was design advice. Can you just explain what that is and how that kind of identifies, I think, suggested improvements? And have you any kind of real life examples of that? Have you had any surprising redesigns off the back of that as well?
Yeah, definitely. I'll share my screen again and give you a live demo. Just
Perfect.
a sec. All right, you should be able to see my screen again.
Yeah, perfect.
Okay, so this is actually the car I designed a long time back, and it was full of errors, the design that I made. So, for example, I had these curved headlights, but there was a pocket of air. So the air would enter the headlights and then need to curve out again around the sharp edge of the headlight, and this would cause flow separation. My bumper, I still had exposed front wheels. So if you look at the surface pressure, you would see that there's still pressure buildup around this outer edge of the wheel. Even though it's a simplified wheel, this was a problem. I had some of these design features. So I had like a setback in terms of the height on the front bonnet, just to give it like a visual cue there, which caused a local dip in pressure and so on. So design advice is an extra simulation which will, based on a standalone set of equations, it calculates backward from your goal, which in my case was to reduce drag. It calculates backward for every element on the surface. Should I move this element outward or inward? So outward is red, inward is blue, to reduce the drag. And then you get advice across the entire surface of your car. So if you look at those key elements, for example, this design feature I had on the front bonnet, the design advice is telling us, well, the edge itself, which sits on the high plane, let's say, this is marked in blue, which means push it down. And the lower plane or the lower surface here is marked in red right after this drop here, which means push it up, which basically means smoothen out this edge. It's not good for aerodynamics. If you look at the lights then, this entire edge of the light here is blue, which means push this inward, which means reduce this opening so that more flow will just hit the light and curve around it rather than get trapped inside and then having to curve around it to go out again. The same for the wheels. So to prevent this flow separation around the wheels that we saw, the design advice is telling us, well, this is all red. Please move the bumper outward so that you cover more of the wheels. And so the entire surface of the car is full of interesting design advice on how to reduce the drag. Same around the A-pillar, for example. Of course, you want to get rid of some of those edges that you have and make your windows flush. It's giving us advice on adding a small kicker here to push some of the air around the tire so it doesn't interfere too much with the tire itself and so on. At the rear is going to give you advice on how to optimize this rear spoiler on your car. So that's a complete overview of suggestions on how to improve your car with one extra simulation.
That's very clever. Wow, that's very, very clever. The capability of that is just absolutely brilliant. So for motorsport engineers then, focused on kind of downforce efficiency, what advanced features help dissect performance at the detail level?
Yeah. So if you look at, first of all, the setup, if you want to optimize the setup of your car, we do have advanced features that will allow you to just run a whole batch of simulations in parallel. For example, if I just go back to the setup that we had. So this is the Renault again. We also have an advanced feature here to set the ride height. So automatically, if you upload a model as an assembly, which means you have your wheels in there, your mirrors, your front bumper, anything, we will actually see those things as separate components, which means we can dynamically change the ride height. Imagine I want to raise the front of the car, for example, just to see what happens if you hit a bump, what happens to the aero underneath the car, or bring it really low down, just to see if you set it up for race mode, what's going to happen. Or if you change the rake angle of your car within the limitations of your race class, you can analyze all of these settings and then just run a whole batch of simulations. So if you want to do a sweep of various setups, you can change the ride height over here, front, rear, and so on. You can just copy paste almost your Excel list of settings you want to analyze, give each simulation a different name, and then just launch everything in one go. So this really speeds it up in terms of the setup time. When it comes to analyzing results, we saw that we had the design advice, which tells you how to improve things. If your class allows you to actually morph your design, you can actually use our morphing as well. So this is an example of how our software can, within a design space, this is an example of a very simple area on an Ahmed body, how it can actually morph your design, which is what you see here. It automatically morphed the rear of this Ahmed body by adding a spoiler at the rear, which is really powerful. This is something that we have applied to Aptera, for example. So Aptera is the solar-powered car that I mentioned. So this car here, yeah, we have too much commercials these days. So I'm getting diaper commercials and car commercials. So yeah, it's a good summary of my life. So if I skip this stuff, we actually went to Aptera to visit them. So this is actually an animation that we made for them. This is the airflow analysis around the car. And then we asked our software to optimize areas around the wheel here, around the tail, and so on. And I'll just skip to that part, which is this one. This is where our morphing actually tweaked the geometry of the wheel covers around their car. And this was really interesting because by intuition, and I would have done the same, these are exposed front wheels. So they are there left and right next to the car in the exposed airflow. They were aligned with the wind direction, with the driving direction, just a drop shape. But then our software was telling the engineers and designers, well, that's not correct because the flow around the main car has already been curved left and right or outward. So by the time the air hits the wheels, it's not coming in aligned with the car. It's coming in at maybe a 10-degree angle because it needs to curve around the car itself. So our software automatically pushed the nose of the wheel covers inward and the tail outward to align it with the incoming flow direction. And that's just one example. We did this in multiple areas. We also went to look at the rear of the car. So here they had like a two-dimensional airfoil profile around the wheel, which made total sense. But in reality, airflow is 3D. So it doesn't just flow horizontally, it also flows vertically. And our software was telling us, well, part of the flow, which is actually diverging towards the lower part here, you also need to add a round in the vertical direction. And so our software did this morphing. This is the actual output of our software that we rendered. And then at the tail, they still had like a cross section for the license plate and so on. Our software told them, well, if you squeeze this further down, you will get less of a cross sectional area of air that you're dragging along. And so this is really powerful. We also applied this to the Lamborghini project that we did. They were able to cut the drag by 15% on the Aptera by implementing these changes, which is dramatic. And then we've got Robin Shoot doing Pikes Peak races, also using our software. And on the Lamborghini that we did, we also optimized the winglets, for example. So these are small wings on top of the car. We actually didn't want downforce on this car because the goal was to have a top speed, which is as high as possible. So you don't want too much downforce because if you have, let's say, 100 kilograms of downforce at 100 kilometers per hour, that becomes 400 kilograms at 200 kilometers per hour because it's proportional to the square of the velocity, the aerodynamic forces. So if you have too much downforce, you will just completely squash the car during a top record run. Which is why we optimize these winglets to have the right balance between downforce but not generate too much drag in the process. So these are features that we apply to race teams. So in terms of the setup, fully automated setup to just launch a full aero map analysis in a matter of a few minutes. And in terms of analysis, as you saw, we have very intuitive tools where we calculate the aero balance automatically. And this is actually the first time we show this publicly. We have a complete redesign of the platform coming up. So this is the new interface with different styling and so on, where you change between pressure and friction map, toggle the streamlines, add the drag to the same plot, and so on. You'll get your downforce values, an indication where you are in terms of drag coefficient compared to other applications, curves that will predict the power and the drag forces that you have at different velocities, and so on. So this is all coming up within a month, let's say. So wow. Here's the first preview, let's say.
Wow. World first on the Driven Engineers podcast. Thank you.
Exactly. Yeah.
You've mentioned the pricing already, and that it's pay per simulation. There's no license, right? So
Yes.
what's the thinking behind that? And I appreciate, like you said, the initial outlay for teams, small businesses to run a license over a 12-month period can be quite extortionate. But
Yeah.
how does it lower the barriers, for smaller teams, startups, or even just hobbyists or individual engineers in the field that
Yeah.
that might look at this?
Yeah. So what we did is we created 3 annual plans. I'll share them here, which are tuned to different, let's say, usage profiles. So you mentioned hobbyists. Well, we have a discovery plan, which is 990 euros for 25 credits, which allows you access only to the basic simulation, which is the low resolution simulation of 1 million cells. You don't have access to rotating wheels or radiators or anything like that, but you can get started on small projects like Formula One in schools, which is about small miniature race cars and so on, which means you can run 25 different analyses using that single plan. If you're, let's say, an individual consultant or you're working for a small race team and you want to get started with at least a few analyses of your car, maybe do a yaw study, maybe do a ride height analysis, different ride heights, then we have a professional plan. This one comes with 100 credits for 2,990 euros, which allows you to run also the regular simulation at 10 credits per simulation. So you can run theoretically 10 of those mid-resolution simulations. You will get access to rotating wheels, radiator analysis, and so on. And you can also get our consultancy at 10 credits per hour. So that means a small team will have access to both software and hardware, because that's all included in the credit cost, and also expertise on our end. So you don't have to take your results to yet another consultant to help you make sense of it. We jump on a call with those customers and explain them how to understand the aerodynamics and give them tips on how to improve the performance of their cars based on what we see. So this is a small scale initial plan that you can go for to just understand your existing car design. And if you want to dive deep into the aerodynamics, like for stock car racing and the Lucas di Grassi project and so on, we have the enterprise plan, which starts at 500 credits for a custom price. So depending on how many credits you need, we'll make a custom plan for you. This one unlocks the advanced simulation, so 100 million cells. It also unlocks the morphing, where our software will start to morph your design and send you back a morphed 3D file. It allows you to have multiple people using the same AirShaper account with their own login, and it allows you to run those sweep simulations to launch ride height in a batch, in a single batch, and set the ride height. Those are all features which are tuned to our larger customers using the enterprise plan. So different tiers depending on your usage, and no license fee, just credits that you can use directly.
Perfect. And I did notice as well that you've got a couple of kind of demonstrator models on your front page as well. So if
Yeah.
people wanted to go in and run a demonstration simulation just to get a real quick understanding what it looks like, you've got that there too.
Exactly. Yeah. On the website itself, you can just play around with models, but you can also make a free account and just check out sample simulations. So there's a database of literally thousands of models that you can check and just play around before even having to spend a single euro.
Perfect. So where do you see the biggest kind of potential for AirShaper then? Is it still racing teams? Is it EV range optimization? Is it concept car development? Where do you see AirShaper fitting in?
Well, there's two answers. Like, one is more of the same because we are successful, so that's a matter of continuing our work in terms of branding, exposure. Our YouTube channel that you've maybe seen, where we're now at around 110,000 subscribers. So if people want to learn more about aerodynamics, that's one of the resources that we provide. So that means more of the same. In terms of markets which are upcoming, for example, or at least booming, in terms of drones, we're doing a lot of work on drones. We do non-weapons drones, just to be clear, but also for civilian applications. There's a lot of work being done on drones to map industrial sites with cameras and everything. So that's a key market for us as well. Electric aviation, just like for cars, electrification is really changing the scene, and there's a whole emerging market. At least many people assume that it's going to be a big market for electric aviation. The cool thing there is that with electric propulsion or drivetrains, the layout of an aircraft can be changed completely. you can now put two motors and propellers on the wingtips because the motors are just
Yeah,
10, 20, 30 kilograms, and that's it. You just need to wire some cables to that point, and you can completely change the layout, the center of gravity, anything of your aircraft. Of course, the batteries are still a huge problem, but there's a lot of movement in that sector as well, which brings those customers to the point of questioning the aerodynamics of the existing aircraft, which makes total sense based on the drivetrains. But now the field is wide open. So we see a lot of improvements there. And then, of course, technology wise, there's AI, obviously. We also have AI on our end. So we have the morphing and so on that you saw, the design advice. Those are examples of how we dramatically speed up the design process for our customers. But then there's also the next step where AI is actually making its own predictions, which is also something that we do together with other companies, where our platform is being used to actually calculate the ground truth, is what they call it. So maybe 100 different designs, and we calculate the ground truth, and then an AI software will build a surrogate model based on that result data set, and then make predictions to get even better at certain aerodynamic operating points.
brilliant. Yeah, that's really good. So you mentioned a few projects already. You mentioned Aptera, you mentioned Lucas. Are there any other projects or stories from the world of automotive or motorsport that showcase what AirShaper can do?
Yeah. So when you go to our website, what you see is not entirely representative in terms of the effort we spend per segment. Of course, we need clearance to show certain things. And one of the key areas where we don't get a lot of clearance, just a few examples, is normal, regular cars, right? So we work for large OEMs as well. They have their own software. They buy their own licenses. They would have dozens of engineers doing this. But in parallel, AirShaper is being used by design studios around the world to dramatically speed up the process because we can work with those early stage surfacing models which aren't watertight. This really empowers designers to go really fast in terms of coming up with a design which doesn't have to be completely demolished by the engineers afterwards because it wasn't sensible in terms of aerodynamics. They can now design something, check it, tune it already, and go to the engineering department and say, can you check this one? And instead of asking the designers to lower the bonnet by 5 centimeters, now the engineers just need to ask them, can you tweak it there and there with a few millimeters? And it's already sound because they already had access to these tools. So quite a lot of customers at AirShaper are in the OEM space, large OEMs, which is companies in America, in Europe, in Asia as well, using or allowing their design studios to use AirShaper as well. And that's what we don't really show too much on our website because it's very confidential work.
Yeah, no, that's good. Completely understand that. The NDAs that have probably been signed as well. So
Yes,
completely understand that.
yes.
I understand that completely. Okay, looking ahead then, you've mentioned the new simulation or the new version that's coming already. Again, world exclusive. Thank you. But looking ahead, what else is next for AirShaper? Where are you guys going
Yeah.
next?
So what we silently released some time back is also an internal flow option at AirShaper. So we can analyze manifolds, for example. So anything where airflow, whether it's compressed or non-compressed or gas or air, going through a network of pipes, for example, or through a turbine or a pump, we can analyze that as well. So one of the most recent videos that we released was for Donkervoort. Donkervoort is a Dutch sports car company, like these open-wheeled, very fun race cars, very close to the ground. So they use AirShaper not just for the external aero, but also to optimize their exhaust manifold. So you have the different runners, which actually evacuate the exhaust gases and bundle them to go to the exhaust, the central exhaust. If you can reduce the pressure resistance for the exhaust gases, you actually give the engine more, let's say, breathing space, if you want to call it that way, which it makes it easier to evacuate gases, which increases the filling of the pistons, let's say, or the combustion area with new air and fuel, which increases engine power. So by just optimizing, so lowering the pressure drop and also equalizing the flow rate through different runners so that all cylinders actually behave in a similar way, we were able to improve engine power by 13.2%. just by improving the exhaust manifold,
Wow.
which is a dramatic result. And you can apply the same philosophy to the intake manifold, which is where you provide airflow, hopefully in a very equal manner across the different pistons. And that's what we do as well. So in terms of automotive, that's definitely an area where we want to branch out and reach more customers. We've also done exhaust noise optimization for retrofits for old Porsches, for example, where they optimize the airflow, which then translated in a different sound signature, which is also really important. So yeah, internal flows is definitely a key area where you will see us grow.
So a lot of our listeners are aspiring engineers, people that are trying to get into the world of engineering, be that automotive, motorsport, aerospace, whatever that might be. But we always ask our guests, what advice would you give them? What advice would you give to your younger self? And anybody that's listening who wants to get into CFD and aerodynamics, what advice could you give?
Oh, of course, I'm just one person. You would have to blend my advice with the advice of many other people with more experience and different experience. What helped me was to just have this side project, which is really a passion. So start with your passion. I would say that is a clear given, because if it's not your passion, you might just burn out or just end up doing something else. So that's one thing. Another thing that I like is just going out there and build something yourself, whether it's physically or digitally. Try and create something of your own. It's great that you mastered your course in aerodynamics or numerical schemes and anything like that. But a lot of people have mastered that. If you want to set yourself apart, imagine you're applying for a job in F1. If you can showcase like, oh, hey, actually in my backyard, I tuned the kart and actually I cut my lap time around the yard of my parents by 2 seconds. That is interesting. It shows that you want to go out there and do your own thing and get creative and just bypass the conventional rules and limits that are out there. When it comes to simulations, you can also do similar things. There's OpenFoam, which is also what we use as the core in our platform, which is an open source library for CFD simulations. It's quite tough to go through. That's what I did before I even started building anything else. I did some one-off consultancy projects, running simulations on a propeller rotating inside a static duct with a gap of 1 millimeter on both sides at the interface of water and air, which was a terribly difficult project. I didn't earn much on that one, but I delivered the results, and it cost me a few nights' sleep.
Yeah.
But it worked. So going through the dirt, as I like to call it, really pays off, because you really get to understand what is the actual pain point. What does it mean to use a different schemes for your solution? When is the simulation stable? When does it crash? How can you solve it? And so on. And even if later on, you're not going to go back to those really core settings, you know that they're there. And when you have a discussion with someone, you can actually frame it against a much more fundamental backdrop. So getting out there, experimenting yourself is, for me, one of the key things that will help you along your path.
Really, really good advice. So we're going to tie things up there. I really, really appreciate your time today. I feel like we could just go on and on, but I feel like we could probably do another episode at some stage.
Yeah.
We're going to do some collaboration work regarding some simulations around some of the Renaults. Just to our listeners, watch this space. We're going to be doing some work around that and hopefully show some of that off shortly and soon. But we're going to wrap things up there. So just wanted to thank you for your time, and thanks very much.
You too, Matt. It's been fantastic. Thanks a lot for this impeccable preparation, and I look forward to the next session.
Good. Take care. Bye for now.
You too. Bye, Matt.